Hi guys, hope all of us are doing great today. So my name is Ernest and this is the Ernest Sciences and Mathematics TV channel. I'd like to welcome each and every one of our members, especially the new ones who have joined the group, and I'd like to encourage us to be active on the comment section. And I'd also like to, of course, welcome more to join us so that we can be able to have a large community of members who are discussing these topics in sciences and mathematics. So for today, I'm going to look at one of the topics in chemistry, and this is the linear combination of atomic orbitals, which basically have written on the board. Now, this basic model is a mathematical expression that is used to try and express this particular overlap of orbitals, and we're going to see later that this particular essence of models are being brought about in trying to explain some of the properties that, of course, we're going to observe being displayed by these different orbitals, or rather combination of atoms to form, of course, molecules. So in a sense, of course, we're trying to explain this particular concept in this discussion. And I'd like us also to go and check on other videos that we have, the previous videos particularly that we have done on different ways of explaining the atomic orbitals and how molecules can be formed. So without further ado, I'd like to welcome each and every one of us into our discussion. So that one said and done. First, I'd like, of course, to express my appreciation for those members who have engaged us on the comment section. And also, I'd like to encourage us to check on our description boxes so that we can be able to get related videos and other uploads that we have done on the same. Now, from the topics that we are going to look at today, linear combination of atomic orbitals. This one gives us, the concept of a linear combination gives us a mathematical aspect that we're going to look into, and therefore this is going to give us an impression that basically this concept deals with a mathematical method of trying to combine atomic orbitals, and this is used to express what we call the resulting molecular orbitals, which we are going to look into shortly. So therefore, the molecular orbitals result from a combination of atomic orbitals, as from the rough description of a topic for today. Now, from our previous videos, we have talked about the concept of orbitals, and basically the atomic orbitals that we have looked into, especially on some of our videos on the concept of hybridization of atomic orbitals. So in this case, the concept of atomic orbitals, as we defined it in our previous video, is a state of individual electron clouds in a single atom, or rather it's a probability or a volume in space where there is a possibility of finding an electron. So therefore, from that particular rough definition, therefore I've mentioned the concept of an individual electron, and I've mentioned the concept of a probability, and this of course is electron cloud, as we can say, as we mentioned that this basically is some kind of a cloud or a wave around an atom where there's a possibility of locating this particular electron. So the concept of probability gives us the mathematical aspect of this particular electron. And they were said that Erwin Schrödinger developed an equation whose solutions are going to assist us to try and define or quantify these energies and the positions of these particular electrons, which basically gave us the concept of orbitals, atomic orbitals. And therefore, from this particular sense, therefore we're going to look at atomic orbitals as these electron clouds, or the volumes in space which whereby there is a possibility of finding electrons. Now, we mentioned the different types of orbitals, and we said that particularly we had mentioned the 4 different types of orbitals, and we had said that these particular orbitals are given by the angular momentum number, from which we had mentioned from different types of quantum numbers that we had discussed in one of our videos. So in a sense, the angular momentum numbers gives us different orbitals, and we had said that we have the s, p, d, and f orbitals that we had discussed in an exclusive way. And we said that these different orbitals, according to specific rules, they have got, of course, from the Schrodinger's equation, we're going to get the volumes in space where this, how we can be able to describe this. And for the s orbital, we said that this basically is a spherical orbital, which we can try to look at as a volume that is spherical in shape. And therefore, we can be able to try and look at those axes as a volume in space. Therefore, from this particular point of origin, which is the middle, this is going to occupy this spherical space that is along the xy, basically, which is in a three-dimensional space. Therefore, it's going to be spherical. And from the second one, we see that the p orbital is going to be having the dampened shapes, as we had mentioned in one of our videos, which are aligned along the axis for the x, y, and z direction. That's just a rough sketch. That is x, y, z. So for the p orbitals, we say that each axis has got an orbital. For instance, if I say this is the x, then therefore we're going to have this one illustrated as the px orbital. Therefore, in this particular sense, there were specific rules. So this is a dampened shape. This is a dampened shape, of course, for the p orbital. And then for the d orbital, we had said that this particularly also assumes some kind of a shape. And this one's aligned on the both the axis. Now, for the p orbitals are aligned along the axis of this three-dimensional space, so as we can perceive them in three-dimensional space, they are aligned along this axis. And for the d orbital, these ones are as well illustrated as such, but they are going to lie along this particular axis and on a plane. And therefore, we can be able to illustrate that one as the d, x, and y. Now, from a geometrical point of view, I hope this is going to give us an insight into how these ones appear. So therefore, we can be able to illustrate the d orbitals using that particular illustration. And lastly, we said that for the f orbital, this is going to be occupying the respective spaces that we are going to have in this particular axis. So therefore, they are going to have some rather complex shapes, which are going to appear as this. So basically, for the next two, they need a three-dimensional perspective for us to try and visualize how they can be able to be represented. Now, in this case, these different orbitals interact with others. Various atoms that possess orbitals are going to interact with others to form chemical bonds. And therefore, this particular discussion concerns this particular a combination of or overlap of these various orbitals, which are going to result in the formation of what we call molecular orbitals, as I had mentioned from the beginning of this particular discussion. So therefore, we can be able to define the concept of a molecular orbital as basically what we are going to refer to the region of space where molecules basically we're going to refer this one to as a region of space where molecules valence electrons are present or are likely to be present. So therefore, just as this is analogous to the definition of an atomic orbital, so therefore the aspect of a molecular orbital as well as a region in space where there is a possibility of finding these valence electrons of a molecule. So having said that, then therefore we are going to see that we can have different classifications, or rather three types of molecular orbitals, which the first one is a bonding molecular orbital, and then non-bonding molecular orbital, and then lastly we're going to have anti-bonding molecular orbitals. Now we're going to use an energy level diagram to try and give a visual illustration of what basically I've referred to those. But if you try to look at the concept of orbitals as an electron cloud from the quantum mechanics perspective, then therefore we're going to have these ones being treated as well as waves, which in an essence then therefore is going to give us some properties of a wave which can be used to describe this concept of a molecular or a combination of atomic orbitals to form molecules. Now we said that one of the properties of a wave is that it can be this is a superimposed. The spellings are okay. They can be superimposed, therefore there's an aspect of superimposition, and therefore this basically means the concept of overlapping, and therefore this overlapping for waves is going to have two aspects of either a constructive interference for waves, or a destructive interference. Now we can be able to look at this specific properties, or two specific properties for this particular approach, whereby we're going to refer to the constructive aspect of our waves as bonding, while the destructive aspect of this wave is going to be referred to as anti-bonding. Now from the energy level diagram, then therefore for these two particular aspects from the wave perspective is going to be visualized as such. Also, sorry for that. This is for bonding and anti-bonding. For non-bonding, we're going to see that these orbitals from the energy level diagram can be given a different illustration. Therefore, from the wave perspective, for bonding, it's a constructive interference of those electron cloud in a sense, which are waves, and then for destructive interference, it is an anti-bonding, as I have given on the board. Now, in this case, we're going to see that basically for the different types of these combinations, there are some specific rules which we're going to see which should be observed for us to have this concept of a linear combination of molecular orbitals. And these are three basic rules which I'm going to just mention before we proceed for that illustration of an energy level diagram. So therefore, these basic rules. So for the first one, we're going to see that for atomic orbitals to form molecular orbitals, n atomic orbitals, n refers to a number. So n atomic orbitals are going to combine to form n molecular orbitals. So therefore there is that coherency that we are going to see that n atomic orbitals are going to have particular number of atomic orbitals are going to combine to form that respective number of molecular orbitals. And then we're going to see that basically this particular rule number 2, then these molecular orbitals are going to combine, of course, to lead to the formation of the three types of molecular orbitals that we said for bonding, anti-bonding, and non-bonding molecular orbitals. So therefore, the combination of atomic orbitals is going to lead into the formation of these three particular types of molecular orbitals. So therefore, in this case, we're going to see that these different atomic orbitals are going to be occupied by electrons. But for non-bonding and for molecular stability, we are going to see that the non-bonding type is going to be empty. So therefore, we're going to see that for the rule number 3, therefore in a stable molecule, this particular anti-bonding orbitals are going to be empty. So therefore, this is going to lead to the stability of this particular molecule. So therefore, these anti-bonding molecules are going to be empty, and therefore this is going to give the aspect of stability of this particular molecule. So therefore, now this concept of a linear combination of atomic orbitals is quite relevant. We're going to find it having wider applications in some of the topics that we have already tackled, and some areas that we are going to look into especially on the concept of, as we have said, this one basically deals with the concept of a combination of atomic orbitals or overlap. Therefore, this is going to give us an explanation to some of the areas in bonding that we need to explain insofar as overlap of orbitals are concerned. And therefore, we are going to explain also the aspect of lone pairs of electrons that are going to be observed in some of the molecules, or in majority of the molecules that we're going to discuss. And then next we are going to see that it's going to explain the excited state of some of these atoms and other. And now among others also we're going to see that it's going to explain the concept of polarization, which we are discussed in one of our videos, of course, insofar as molecules and atoms are concerned. So therefore, lastly, if we try to look at one of the examples of a combination of these atomic orbitals, of course, we're going to have other examples which are going to follow after this discussion, but for now, we are going just to have one example of a bond of one of the dihydrogen dihydrogen formation insofar as this linear combination of atomic orbitals is concerned. And this basically is a formation of the molecule of hydrogen, which we basically refer, this is a diatomic molecule that we're going to look into. So in this sense, we say that hydrogen is having the 1s orbital, therefore it's going to have a spherical orbital, which we are going to illustrate using this. So for it to form a diatomic molecule, then therefore we're going to have these two hydrogens with an electron there bonding together to form a molecular orbital. So therefore this is going to, of course, be visualized as such. So those two spherical molecules, atoms, are going to form a molecule, a diatomic molecule of hydrogen, which is going to be given as that. So therefore it's going to have this particular shape. So, and this is going to result, we can be able to see that this is going to result from an aspect of a wave, it's going to result to a constructive result of a molecule, and therefore this is going to be referred to as, this is an overlap of these orbitals, which we refer to as a sigma bond, and therefore it's going to contain two electrons which have combined together to form that particular molecule. And if you can try to look from this, we had already been we are conversant with this way of representing this particular reaction. You can just be able to give it as such, or the normal way that we have been giving it in the normal equations. We have always been using this dash to represent the bonding for this lone two pair of electron. Now we're going to advance this one into this display for atomic orbitals, and therefore that is how we can be able to visualize. Now, having shown this, that this sigma bond that is forming, and therefore we are going to refer to this one as bonding orbitals from the three different types that we had mentioned. So therefore, as well, we are going to have what we refer to as anti-bonding orbital, which basically are going to be contained in the higher level energy of as energy level diagram that we're going to show. So for this anti-bonding orbitals, they are going to have a characteristic, of course, which we can be able to display as such, and they have no relationship with this particular atom. This is just put it as such. So this is the anti-bonding orbitals, which we can be able to illustrate using that. So therefore, as we have illustrated that the bonding orbital is this is a sigma 1. This is going to be an anti-bonding, which we said basically for this particular molecule to be stable, then therefore it is going to be empty, and it's not going to contain or have an electron in that specific respect. Now, one of the characteristics of this is that it is going to be displayed in a low energy, particularly on the energy level, and this is for high energy position for this particular anti-bonding orbital. So this is a way in which we can be able to visualize the hydrogen formation in this particular aspect for the bonding and antibonding. Now this is a covalent bond that has been formed in this particular case, where we can see that there is a sharing over the 2 electrons for the hydrogen respectively. Therefore, as we said, since only this particular bonding orbitals are the ones which have been occupied, and the antibonding ones are empty, therefore the molecule is going to be regarded as stable. Now, if we can try to illustrate this one using an energy level diagram that I had said, therefore we can be able to illustrate this one as now, from my illustration, we have been using this particular concept whenever we were talking about spin, but of course we can be able to just give this emphasis for this illustration, that this particular, this is an electron. This arrow is going to imply a single electron. So therefore we can be able to see that in this particular kind of illustration, this one depicts the concept of energy. So therefore this is the direction of increase in that energy level. So therefore, as we have explained, the sigma bond is going to form what we refer to as bonding orbital, while the sigma bond with the steric is going to show antibonding orbital. Therefore, if we try to look at this, I said that I had mentioned earlier that this is going to appear in the low energy. Of course, from this particular diagram, we can be able to see that this is a low energy level and this is a high energy level. So for a stable molecule of this dihydrogen formation, we're going to see that this is going to be the illustrative way of trying to show that energy diagram, which is going to, of course, provide a stable molecule, and which is going to allow, of course, for the concept of reactions with this particular diatomic or rather dihydrogen formation to interact with other molecules. So in this sense, of course, this particular concept of a linear combination of atomic orbitals, we're going to have it expanded into other concepts, which are going to assist us in describing molecules in 3-dimensional aspect and other related areas. So therefore, I hope that this is going to assist us whenever we're trying to give a mathematical representation of these atomic orbitals. And this one, in combination with other related, of course, topics, are going to assist us in understanding other areas that we're going to encounter, especially in trying to describe the Haeckel's theory. This is on molecular orbitals, which we are going to see later under our discussion. So in this case, of course, as I had mentioned earlier, this was one of the models, and of course this was an idea that was 20th century, and this particular model is, or rather, be associated with others in trying to explain this particular concept. So therefore, from its origin from the Robert Mulliken and the Friedrich Hunt, so this was this is the Mulliken and Hunt explanation, Friedrich Hunt explanation, who advanced this particular model in the area, in the 20th century. And therefore, we're going to see that in combination with the other ideas, this is going to assist us explain the Haeckel's theory that we have said on concerning the molecular orbitals. So I stop there for today. I hope that this is going to assist us understand the concept of molecular orbitals, and also to try to visualize how we can be able to represent that one insofar as energy levels are concerned. So that is it for now, guys. Bye. God bless you.